Testing. Testing, testing. Testing, testing. YouTube volume works. See Twitch. Does Twitch work? Testing, testing. Twitch works. All right. And the last one that's left is x.com. How's it going, Every Dream? How's it going, John? See if this is actually going to be live. Okay. I think we're live on all three, and all three of them are working, so let's give it a second here. Make sure this is all good. Still not seeing it on X. Okay, we'll debug that later. It's not super important. How's it going, Ed? How's it going, 87 GM? How's it going, you, June? All right, let's go ahead and get started. I got a new horn for you guys here this time. This one is it's called an Israeli shofar horn. It's made out of a goat horn, I'm pretty sure, something like that. It doesn't sound anywhere near as good as the didgeridoo, so you guys better be ready for this one. It sounds terrible. All right. Now that I blew your guys' eardrums out, today we're going to be looking at InstaFlow. So InstaFlow is a paper released on 12th September 2023, so relatively recent paper coming out of Department of Computer Science, UTexas at Austin, which is actually close to where I live. And it's a joint partnership with Helixon Research, which I actually ended up looking up, and it's kind of weird. It's like a protein company. So it's like applying, I guess, AI and ML to proteins. I don't know why someone associated with this would be publishing a paper about stable diffusion, but okay, you know, I guess you do what you do. But I think the main person of interest here is this guy here, Qiang Liu. And Qiang Liu, if you actually go and look at some of his previous work, he's already done basically papers on this. He calls it Rectified flow, and you can kind of trace this back all the way to papers such as neural ordinary differential equations, where people use ODEs for different types of things in neural networks. But this is the main paper, right? This is the same guy, Qiang Liu. I don't know how I'm pronouncing that right. But this is basically that paper applied to stable diffusion. And this entire paper is basically has this GitHub page. Unfortunately, they don't have anything on this GitHub page yet. If you notice, there's basically just a README and a license, so they haven't pushed any code yet. But if you scroll all the way to the bottom of this GitHub, they mention that basically the training script comes from a modified version of one of these fine-tuning examples in the diffusers. Diffusers is the Hugging Face library that Hugging Face uses for stable diffusion, and this is the actual training script. So I imagine largely what they did with this research, or at least what this person did, is basically I think probably one of these people, right? The first authors are the ones that do the work, and then the last author is the one who kind of is the professor. So the professor has this idea, it's kind of like his pet idea, and then he gets these two people here to basically implement it in the training script of diffusers. So we don't have their training script yet, but it's basically probably just going to be this with some modifications such that it uses this rectified flow. All right, let me take a big sip of this coffee and then we'll get started. Diffusion models have revolutionized text-to-image generation with its exceptional quality and creativity. Already some issues there. That should be their exceptional quality and creativity. However, it's a multi-step sampling process. So what do they mean by multi-step? They mean that diffusion models require multiple steps, right? Iteratively removing noise such that you go from pure noise to a image. So you have this kind of multi-step process, and that multi-step process often requiring tens of inference steps. We've seen it as high as 1,000 steps, but that slows it down, right? It means that you can't really run these diffusion models super quickly because you basically have to auto-regressively kind of keep sampling and keep performing inference until you finally get to the final image. Yeah, I don't think it's a lack of grammar. I think it's just ESL, right? Obviously, all these guys here are potentially not. You see these .cn Chinese emails, so they're definitely English second language. So you can make fun of them for not knowing English well, but they can make fun of you for only knowing English. So it's a double-edged sword. Previous attempts to improve its sampling speed and reduce computational costs through distillation have been unsuccessful in achieving functional one-step model. So what are they talking about here about distillation? So distillation is something that we run into time and time again. There's different definitions of distillation. There's dataset distillation, model distillation. In this case, what they're referring to is this type of distillation. So distillation is when you take a big teacher model, right? And that teacher model takes some input and then produces some outputs. And what you do when you distill something is you create a smaller, usually smaller, right? Because the whole point is to make a smaller, cheaper version, and you call it the student. And the student doesn't get trained the same way that the teacher got trained, right? With some specific loss and so on and all this other fancy stuff. It basically just gets trained to mimic the teacher. So what you do is you give the same training data to the student, and for every single one of those, you say, okay, you should have predicted the same thing that the teacher predicted. And basically what ends up happening is that the student ends up being a pretty good approximation to the teacher, despite only being a smaller size, right? And this is distillation in the idea of like taking a teacher model and then making it smaller into a student model that's almost quite as good, but not quite as good, right? But it's significantly cheaper. But what they're talking about is that people have had this idea of distillation. This is a paper called Progressive Distillation for Fast Sampling of Diffusion Models, where people take the same idea of distillation and they use it to reduce the number of steps. So you see here how each of these green arrows represents basically one of these steps, right? So 1 green arrow, 2 green arrows, 3 green arrows, 4 green arrows, 5 green arrows, right? That's how many steps you need in order to create that final image. So in progressive distillation, they're like, okay, we have a teacher model that requires 4 steps. Can we have a smaller in terms of the total amount of inference steps model, distill from that something that only takes 1 step, 2 steps, 1 step, and then go all the way, right? And you can basically reduce the total number of steps required down to hopefully just 1 step, although in this case it's not going to be just 1 step. But you're now distilling a diffusion model to reduce the total number of steps, which you can kind of conceptually think of like similar to the idea of distilling here, where you're distilling a larger model to be smaller. So this idea of distillation is basically concentrating, right? Distilling in the analogy of alcohol production is whenever you take a volume of liquid that is kind of a lower alcohol percentage and you distill it down into a smaller volume of liquid that has a higher alcohol percentage. So it's the same kind of idea. Okay. So people have tried distillation and tried that as a method for reducing the total number of inference steps you need to generate an image, but it's kind of unsuccessful in achieving a functional one-step model. So that's not necessarily the right way to do it. Okay, so what are they going to propose? In this paper, we explore a recent method called Rectified flow. And here you go, citing his own work there. So he gets a citation for his paper as well, and just like that, his academic credentials increase, his academic powers. So he cites his own paper here, Rectified Flow, which turns so far has only been applied to small data sets. The core of Rectified Flow lies in its reflow procedure. This is kind of a word that's going to keep coming up over and over again, which straightens the trajectories of probability flows. And this is basically the high-level idea of this entire paper, but it's going to take us a while to like explain exactly what's going on there. So I'm going to come back to that. I'm just going to finish this abstract, and then we'll go back to what exactly straightening a probability flow trajectory even means. Which refines the coupling between noises and images and facilitates the distillation process with student models. Here's your student models, right, which come from this distillation process. So you're kind of seeing what they're going to do. They're basically going to distill from a stable diffusion model. They're going to distill a one-step diffusion model that where that distillation process is going to involve this rectified flow kind of process. We propose a novel text condition pipeline. Text condition, again, just means that whenever you're performing your diffusion, right, here you're removing the noise, right, you're conditioning that on some piece of text. So what does that mean? It means that here's our good old diagram of a diffusion model. This is a latent diffusion model, so you're diffusing in the latent space of images. The latent space of images is basically just a compressed version of the image that is created by this encoder, and then you can always go from the image space, x0, to the latent space with the encoder, and you can go from the latent space back to the image space using the decoder. So that's the encoder and the decoder. But text conditioning is whenever you take some text, such as the text that you would use to generate the image, right, in stable diffusion, a picture of a beach with the sun, right, and you feed that through a text encoder, it turns into like a little representation, and then every time you remove noise from this latent with this unit, you're conditioning that with that piece of text. So by changing that piece of text, you can basically change the noise that gets removed, and by changing the noise that gets removed, you get an image that is semantically related to the text, right? So that's what they mean by text conditioning there. To turn stable diffusion into an ultra-fast one-step model, so there's your distillation, right? They're distilling the big stable diffusion model into a small one-step model, right? So this kind of idea of progressive distillation, where rather than having your big stable diffusion, which takes 10 steps, right, to finally create that final image, starting from noise and then going to the image, you're going to distill it into a model that starts directly from the noise and then in one step just goes straight to the image. Okay, in which we find reflow plays a critical role in improving the assignment between noise and images. Okay, leveraging our new pipeline, we create, to the best of our knowledge, the first one-step diffusion-based text-to-image generator with SD-level image quality. So there's kind of the result, right? So why do people care about this paper? Because it has great result. And what is the great result? Is that you can get stable diffusion level image quality with just one step, achieving a Fréchet inception distance of 23.3 on MS Coco, surpassing previous state-of-the-art techniques, progressive distillation by a significant margin. Okay, so it's better than progressive distillation. Utilizing an expanded network with 101.7 billion parameters. Let's go ahead and use our blue to highlight that. We further improve FID to 22.4. We call our one-step models InstaFlow. On MS Coco, InstaFlow yields a Fréchet inception distance of blah, 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 and outperforms StyleGAN-T, which is a more modern variant of generative adversarial network. I do believe that, I don't know if it was this one, but we did do a live stream on one of these more modern GANs, so check that out if you're interested in GANs. And then in terms of the actual training, they did this on 199 A100 GPU days, which is not, that's definitely within the kind of bounds of academia, right? This is not like an industry level research budget, but that's not insignificant either, right? I feel like sometimes we read papers where everything is done on a single 3090 GPU, and that's, you can kind of see the flavor of like, okay, this is one student working on one GPU, and they're kind of doing probably some kind of LoRa or something. This paper is definitely more significant. You're talking about a cluster of A100s, a significant chunk of time on that cluster. So I bet you it wasn't even probably the University of Texas at Austin. It was probably this Helixon research that paid for this stuff. Okay. So here we have a little figure that kind of explains what we've seen here, where stable diffusion takes a bunch of steps in order to get from the noise into the image, but InstaFlow goes from noise straight to the image. InstaFlow is the first high-quality step. Within 0.1 seconds, let me just make that blue, it generates images with a similar FID as StyleGAN-T on MS Coco 2014. So we keep coming up to FID over and over again on this channel, right? FID is a very popular metric. MS Coco is a very popular data set, but I was like, you know what, why don't we dive a little deeper on that today, because I feel like a picture's worth 1,000 words, and I went ahead and I found that for you. So this is what Fréchet inception distance actually is. What Fréchet inception distance actually is you take an image, you feed it, or two images, right? And then you feed them into an inception model. This is a very old convolutional neural network based model, and V3 just refers to, it's a version 3, right? There was an inception V1, inception V2, inception V3. So you feed images into these inception V3s, and then you look at the output, right? So basically you can think of it like the latent, right? Much like here in a diffusion model, you have this encoder which is turning the image into this little latent. The same kind of thing is happening here with an inception V3 model, where it's creating this kind of feature which represents that image. So then the Fréchet inception distance is just how close is this feature to this feature? How similar are the images by using the distance in feature space as kind of the distance semantically between those two images. So that's all Fréchet inception distance is. Here's some examples of kind of how Fréchet inception distance changes according to different transformations. So here you have the distance between this image and this image is this, the distance between this image and this image is this. So you can see how like it's a little bit weird, right? There's a little bit of a weird relationship, how like this image and this image are much more similar than this image and this image. So like something here kind of just fundamentally breaks the inception feature. And that's kind of the reason I don't like this. I don't like the FID score because it's not a good metric. It's not smooth, and I don't think it's... I just feel like it's an old network. I think that this inception V3 model is very old. It has its own kind of problems, and by using it as a distance metric, you're just kind of introducing more issues, and it's also not a very understandable or readable number, right? So whenever someone tells you it reduces the Fréchet inception distance from 37 to 23, like, I don't know what that means, right? That's not a number that a human can really understand very well, right? So I don't know. I'm not a huge fan of FID, but it is something that pops up again and again and again because it's very easy to calculate, it's very easy to quantify, and there's kind of a historical legacy to it, right? So people have been using it for years and years and years, so therefore it's very easy to say, let's just keep using it. So that's a little side tangent on what Fréchet inception distance is. And MS Coco, that comes up time and time again. MS Coco is a common object in context. That's what the common object context, COCO, and it's basically just pictures of things. Like, and the context refers to the fact that it's not just a picture of a dog with an imaginary background. It's a picture of a dog in a pen or a dog on the grass, right? So they're in context. It's like objects that appear in the real world, but they're also in like a context that like is appropriate to that object. And this was made by Microsoft all the way back in 2014. And you can use this for segmentation. You can use this for classification. It's kind of just a generic image data set, and people use it here. So whenever they say Fréchet inception distance for MS Coco, they're trying to pretend that MS Coco is representative of all natural images, and that Fréchet inception distance represents the distance in that space of all natural images. I think there's issues with that, but it's kind of a standard. Okay. So whole fine-tuning process, blah, 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 costs only 199 A100 GPU days. I don't know about this only. I wish I had 199 A100 GPU days to burn. Here we have log time to generate one image. So obviously InstaFlow is very fast. It's comparable to StyleGAN-T, right? A generative adversarial network only takes one forward inference in order to produce the image, right? In a generative adversarial network, you have your generator and you have your discriminator. Your generator basically creates the image from some noise or something like that. And in one shot. And so you see how basically InstaFlow is just as fast. Here they're comparing to progressive distillation, which also... All right, we're back. I think we're back. Yeah, we're back. Okay. Sorry about that, guys. Okay. So here we have some pictures of good old InstaFlow here. Obviously, this isn't like super high quality necessarily, but I think they actually distilled it from Stable Diffusion 1.4 or something like that. So it's not even the most recent version of Stable Diffusion. So I don't know. It's not that bad. Here they also feed it into the SDXL refiner. The SDXL refiner is an additional model. So the SDXL paper, which we read on this channel as well, has kind of the standard Stable Diffusion pipeline, but then it also has this additional kind of refiner model that'll basically just crisp up the image a little bit. So here they've basically fed an image from the InstaFlow 0.9b, where 0.9b is obviously the number of parameters, and then they fed it once more through the refiner to just make it a little bit crispier for these nice, clean images here. We got an eagle, we got a panda. It's looking good. Inference time measured with an NVIDIA A100 GPU, about 0.12 seconds, which is super fast. They have a nice little GIF here on the GitHub that shows you just kind of the speed here. So this is InstaFlow 0.9b compared to Stable Diffusion 1.5, which is the model they distill from. So again, don't judge the quality of these images to something like a Midjourney or any of the Stable Diffusion XL. Compare it to Stable Diffusion 1.5, and you can see here just how much faster. It's almost like 10 times faster, right? Because it only has to do one step. Okay. Introduction, related works. Let's do a little bit of introduction. Modern text-to-image T2I generative models, DALL-E, ImageGen, Stable Diffusion, StyleGAN-T. DALL-E is OpenAI's model, ImageGen is Google's model, Stable Diffusion comes from Stability AI. StyleGAN-T, GigaGAN, I don't remember what organization those are affiliated with, but basically, you're cool. You can make images. Awesome. Stable Diffusion requires more than 20 steps. That's going to mean it's slow. Therefore, we're going to want to basically make it faster. How do we make it faster? Well, we could just use a GAN instead. That'd be great. Or another way we could do it faster is by reducing the total amount of steps. People have tried to reduce the number of steps with progressive distillation, but in this paper, they're going to be using this reflow concept, and the reflow concept, or rectified flow, is going to be better. So, present a novel one step. Primary issue stems from the suboptimal coupling of noises and images. So you're going to see this word coupling come up again and again. Coupling is another one of those words that has a ton of definitions, right? Everybody, when you think of coupling, my first kind of mental image is like a little piece of metal that couples together two pieces in some kind of engine or something like that, you know, like a couple. But this is a very specific definition of coupling, which is more related to statistics, and we're going to get into that. To address this, we leverage Rectified Flow, an advancement in generative models that utilize probabilistic flows. In Rectified Flow, unique procedure known as reflow is employed. Reflow gradually straightens the trajectory of a probability flow, thereby in reducing the transport cost between the noise distribution and the image distribution. So let's get into this. What the fuck does this mean? The trajectory of probability flows, right? So to do that, we're going to have to take a little detour into what's called optimal transport. Okay, so this is a video on YouTube here from this guy, Gabe Kahn. Only has 733 subs, which is a little sad because this is a very great video. So, and you can find the link to this video along with the link to any of the other things that I show here on my GitHub. There's a GitHub called Stream Docs here, and here's all the links if you guys want to go and look at those. But optimal flow comes from this ancient French dude. And this ancient French dude was tasked with basically building a castle, or he was thinking about building a castle, and he was building this castle, and then there was a quarry, right? And in this quarry, there's a bunch of stones. And he was sitting there and thinking about, okay, how do I get all of these stones to build this castle, right? If you think about it, there's a trajectory that every single stone has to take in order to end up in the castle, right? So one way to do it would be to take the whole mountain of stones and just move it over to where the castle is going to get built, and then just kind of slowly move the stones, but then you're doing, like, if you think of the trajectory of each stone, it's not very optimal, right? It's like the stone is moving here into like a temporary area, then it's moving here, and then it's moving here, and then it's moving here. And that matters, right? Especially if you're back in the, whatever this is, 1700s, 1800s, and every single time you move one of these stones, there's a guy with a wheelbarrow there who's like moving the fucking stone, right? So it's very important back then that the path that each stone takes from the quarry and the big pile of stones here to the final castle is small, right? You want that kind of stone to only move really in a very straight line from where the quarry is all the way to where its final resting place is. And that's where optimal transport comes from. So obviously we're not dealing with castles and stones anymore. What we're dealing with is basically probability distribution. So I think there's a little animation here that I'm waiting for, but you can see here how every single part of this every stone inside this quarry and this mountain of stones has to end up at some place in the castle, right? And how do you do that optimally? That's the whole point. So in this case, we're no longer going to be dealing with a castle and a pile of stones. Instead, you could think of it as two probability distributions, right? So there's one probability distribution, and then you want to move from that probability distribution to another probability distribution. And I think this is a nice little visual here in this part of the video here. Let's see. Yeah, so here you have a probability distribution, this color here, I don't know what this is, or purple or pink, right? And then you have this distribution here, this blue one, right? And you're moving from this purple distribution to this blue distribution. And you can kind of ignore some of the other crap here, but you're basically, there's a transport, and eventually you can calculate the optimal transport between every kind of point in this first distribution into the second distribution, right? So you're kind of like moving from one distribution to another distribution. And what does that mean for diffusion models, right? What does that mean when you're moving trajectory of the probability flow? Well, deep in this paper, there's a figure that I think is actually much cleaner that kind of shows this. Here it is. So the straightening effects of reflow. So let's say you had this part here, right? You could think of this as being a image distribution, right? And that the same way that here you move from this pink, then to this, then to this, then to this, then to this, then all the way you get to this blue, right? You're going from this pink distribution all the way to this blue distribution. The same kind of thing is happening here in your diffusion model, right? You're starting from this distribution, which is just pure Gaussian noise, and you're moving to this distribution, which is the true image distribution. But in between, there's kind of all these intermediate distributions, right? So you're kind of taking this path, very similar to how you start with the pile of rubble, the pile of stones in your quarry, and you want to end up with a castle, right? And the way that diffusion models work now is that path is not straight, right? You're taking every single pixel there is not really taking a straight path to the final pixel value, right? It's kind of like maybe it gets a little darker, and then it gets a little lighter, and then it gets a little bit more red, and then it gets a little bit more blue, and then it finally ends up here, right? So if you were to actually look at the path or the trajectory that this distribution here is getting to this distribution, it's not straight. It's 'cause there's a little bit of kind of meandering about, right? So the whole idea of reflow, which is basically this type of optimal transport applied to kind of distributions, is that, hey, why don't we straighten out these paths, right? Is there a way to basically use all this fancy optimal transport math to say, let's straighten out, let's go from this pixel all the way to the final pixel value without taking this kind of meandering path? And if we do that and we apply that constraint and that kind of cost where you kind of have to move as straight as possible, eventually you can basically one-shot it, right? So rather than going through this step where you're taking the stone and then you're putting it here into this prep area, and then you're moving it to that prep area, and then you're moving it to this scaffolding, and then moving it to that scaffolding, and then finally putting it in the final place on the castle, you basically move the stone in a straight path from where it was sitting in that quarry all the way to the final castle, right? And that's the magic of optimal transport, and that's what reflow is all about here. So hopefully that kind of explains it to you guys. If not, I don't know, but that's kind of the best explanation of optimal transport and what it means in this case. So back to, I think one more thing that we need to define here is a coupling. So a coupling is basically just a kind of a map between this probability distribution, the pile of quarry rubble, to the castle, right? So here they have a little animation here, which is quite nice. These animations are top tier, by the way. I don't know who this guy is, Gabe Khan, but like S tier animations here. So you have probability distribution A, probability distribution B, right? Rubble, castle, noise, images, and this relationship here between them is the coupling, right? The coupling of pi, and then you have these two, here's the actual formal mathematical definition of it, a coupling of mu, which is one distribution, and nu, another distribution, which is just this fancy V, is a measure pi. A measure is just like anything that gives you the distance between two things in the space of x cross y, so this is the x cross y space here, such that the marginal distribution of x is mu, so this is the initial and the final distributions stay the same, right? That's what they mean by marginal distributions, is it doesn't change them, but that's the coupling right there, right? That's the mental image that you could think about with the coupling. And if you actually move forward a little bit, I think the animation actually shows you, there you go. Yeah, here's the little animation that I'm looking for. You can see here how every single little part of X has some optimal ending place in the final distribution. And then everything in this example is the pile of stones and the castle, but in the case of diffusion models, you could think of it as kind of image space, right? So you have some distribution of pixels and images here, and some distribution of pixels and images here. Okay. Now let's go back up. Now that we've looked at that and we kind of have an idea of what it means by straightening the probability flows, let's go back up and let's read the rest of this. Okay. Related works, diffusion models. Diffusion models have achieved unprecedented results. Most of the works are based on stochastic differential equations. Researchers have explored techniques to transform them into marginal preserving probability flow ordinary differential equations. So marginal preserving means that the distributions are the same, right? So that's the marginal there. Marginal distribution. It's marginal preserving. Probability flow, right? So you're flowing from one probability distribution to the next probability distribution. And then ordinary differential equations. A differential equation is just an equation. It's equations that represent the differential, or basically the derivative of something, right? So why are we using ODEs? The whole point of using ODEs, I think I have an example here, maybe this. Where is it? Here we go. So an ordinary differential equation might tell you at this, so you have some function y, right, which in our case you could think of it like the trajectory that that every single little pixel takes to get from the noise all the way to the final value of that pixel, right? And you could have some differential equation which tells you the slope at that, or the derivative at that point of the function, right? So at this point in time, this is what the derivative is, right? And the ordinary differential equation, you could plug in any time and it'll tell you what the derivative of y is at that, right? And the reason that's useful is because you could say, okay, well, if I know the ordinary differential equation, I can just ask it at a couple different points and then get an estimate of the final place, right? So I can say, what's the derivative here? And ODE will tell you, this is the derivative, this red line. And you're like, okay, I'm going to traverse a little further and I'm going to assume that this derivative is true for some small delta t here. And then I'm going to ask it again, okay, at this delta t, what is the derivative? And it's going to say, okay, this. Okay, so I'm going to travel a little further and do that. And then you're not going to get a perfect guess, right? If you could query this ODE an infinite amount of times at an infinitely small time step, then you would get to the final answer perfectly. But you're not going to do that, right? You don't have time to perfectly use the ODE an infinite amount of times. So you can use it a small amount of times and you're going to get some guess as to the final location, right? And this idea of the ODEs is going to be a huge corner piece of what they're going to be doing here with these reflows. Recently proposed to directly learn the probability flow ODEs by constructing linear or nonlinear interpolations between two distributions. These ODEs obtain comparable performance but require much fewer inference steps. Among these approaches, Rectified Flow introduces a special reflow procedure which enhances the coupling between distributions and squeezes the generative ODEs to one-step generation, right? So they ultimately want the 1DE, or they want the ODE to basically give them one step. They want to be able to look at this ODE, and rather than the ODE kind of, you have to try it 4 times, and you try it 4 times and it gives you kind of an okay guess, it basically just one-shots you to the very last thing. So the ODE, they want it to go directly from here to here, right? They don't want to have to do this kind of like multi-step crap going on here. Okay. The effectiveness of reflow has only been examined on small data sets like CFAR10, thus raising questions about its suitability. In this paper, we demonstrate that rectified flow can indeed enable high-quality one-step generation in large-scale text-to-image diffusion models, hence bringing ultra-fast text-to-image foundation models with pure supervised learning. Okay, so what this paper promises, if this continues to hold, obviously this is just for Stable Diffusion 1.5. The quality is not quite as good as the original Stable Diffusion 1.5, so there is you are losing a little bit of quality, but it is significantly faster. So maybe you can just keep pushing down this door of research, keep exploring this particular research tech tree, and eventually figure out that there's a way to kind of formulate these diffusion models such that you can do it in one step, and it gives you pretty much the same exact quality. Okay. Large-scale text-image generation. Early research focused on small-scale data sets, leading to advancements. DALL-E was pioneering transformer-based models, blah, blah, blah. A series of new methods emerged. GAN inversion, GAN-based approaches. Stable Diffusion is an open source. GAN-based models like StyleGAN are trained to adversarial loss to generate high-quality images rapidly. Our work provides a novel approach to deal with ultra-fast, one-step, large-scale generative models without the delicate adversarial training. So what do they mean here is that these generative adversarial networks like StyleGAN and GigaGAN are trained with an adversarial loss, and what that means is that there's basically an adversary. It's called the discriminator, but there's a generator and there's a discriminator. The discriminator tries to detect if something's fake or real. The generator just generates images, and by kind of weaving in the generated images with the fake and real images, you basically can get this adversarial loss, which allows the generator to get better over time. But the problem is that you're creating this kind of like adversarial game between the discriminator and the generator, so that if those ever fall kind of out of sync, right, if the discriminator gets very good before the generator gets very good, or vice versa, you have issues. And if you've ever trained GANs, it's a huge pain, can always end up poorly. So GANs are kind of a pain to train, and that's why they mean by delicate adversarial training here. Acceleration of diffusion models. Despite impressive generation quality, diffusion models are known to be slow during inference due to the requirement of multiple iterations to reach the final result. To accelerate inference, there's 2 categories. You have fast post hoc samplers. Samplers can reduce the number of inference steps to 20 to 50 steps. However, relying solely on inference to boost has its limitations. Distillation is the other approach, which we're looking at there. Progressive distillation is a special type of distillation and produces 2 to 4 step stable diffusion, but in this paper, right, it's a 1-step. Consistency models are a new family of generative models that naturally operate in a 1-step manner, but their performance on large-scale text-image generation is still unclear. Instead of employing direct distillation like previous work, we adopt rectified flow, which utilizes the reflow procedure to refine the coupling between the noise distribution and the image distribution, right? So you have your image distribution, which is your castle, right? That's where you want to get to. And then you're starting from the noise distribution, right? Which is your pile of rubble in your quarry, right? And this reflow procedure is basically refining this coupling, which is that relationship between them, right? Here's the picture of the coupling, right? It tells you how every single little stone inside this noise is going to end up in the castle, right? And anytime I say castle and pile of rubble, think image and pure noise here. So going from pure Gaussian noise to the castle or the image distribution. Methods. Large-scale text-to-image diffusion models and the need for efficient inference. Stable diffusion, open source model, gained widespread popularity. Because of its recurrent nature, what do they mean here by recurrent? The fact that it basically needs the previous time step. So right? This is recurrent and you need to calculate it. Much like a recurrent neural network, you need to basically calculate everything beforehand in order to calculate the next step. Diffusion models are recurrent in that same way, right? Where it's like you can't start from here. You need this to get this, and you need this to get this, and you need this to get this, and you need all the way back, right? Usually takes more than 100 steps, a series of post-hoc samplers, blah, blah, blah. Okay, still an open problem. Okay, kind of a little bit verbose here. They keep kind of saying the same thing over and over again, but let's actually get to the meat of it here. And now they're going to introduce rectified flow and reflow. Rectified flow is a unified ordinary differential equation-based framework for generative modeling and domain transfer. It provides an approach for learning and transport mapping T between two distributions. So you have your distribution, pi naught and your distribution pi 1. So pi 1 is going to be your image distribution, pi naught is going to be your noise. So here you go, pi naught is usually a standard Gaussian distribution, and then pi 1 is the image distribution. Because we could probably get rid of this green stuff here because we got better definitions there. So we use green to define math definitions, and then you have this mapping T. So T will map you from pi 0 to pi 1. So you can think of T as basically like back in the original castle pile of rubble analogy, it's basically a plan for how every single little stone is going to move from the pile of stones to the castle. In this case, it's basically a mapping that's going to say this pixel is going to go from this value, which is the noise value, into the final pixel value in the image. Rectified flow learns to transfer pi naught to pi 1 via an ordinary differential equation or flow model. So here is your ordinary differential equation, right? You have z naught from pi naught and then z1 from pi 1. So here you're sampling an image, right? So here you're sampling noise from the noise distribution, you're sampling an image from the image distribution, and here's your ordinary differential equation, which you're saying, what is the derivative of z of t with respect to t? So your partial derivative of zt with respect to t, and we're going to say that is some function v, and then, of course, the magic is that we're going to basically say this function, we're going to pretend it's a neural network, right? And that's kind of like, anytime you see people setting things up like that, that's usually what they're doing, is they're going to say, we're going to replace this function that we don't know with a neural network, right? I think down here, V is parameterized as a deep neural network. Okay. V, RD cross 0, 1. So what does this mean? The 0, 1 here is the time. So here you have time equals 1, and then time equals 0, right? So you're going, there's the dimensionality D, you could think of it like the actual total number of pixels, if you want to think of it that way, right? It's just the dimensionality of these spaces, and the cross there refers to the fact that you have this time from 0 to 1. So it's a velocity field learned by minimizing a simple mean squared objective. What does a velocity field look like? I like the picture here. So this is a different type of neural ordinary differential equation, but I really like their picture of what a velocity field looks like. This is what a velocity field looks like, right? It's just a bunch of vectors inside some field of vectors, right? So at every point here, you can say there's a flow, right? So in this case, it's going to be more like this, right? You could think of it like, let's go back to the picture that I liked. This one here. Yeah, this one. So you can think of it like this, right? So you're going from time 0 to 1, and obviously this is just a subset of the pixels, and the pixel value is not just a one-dimensional thing here. The pixel value would be R, G, and B, but you could think of that imagine in the background of this, something that looks like this, right? Basically arrows that are telling you where the flow is, right? So rather than you kind of taking discretized steps and then kind of taking this meandering path all the way to the final image distribution from the noise distribution, you could think of like there's some function that basically is the mapping, and this mapping, if we were to look at it here, it would basically look like little arrows at every single point here, right? An infinite amount of arrows that kind of all point you into the final direction of where that pixel is going to end up. It's a little confusing, but I think that the reason I keep going to these images is because it gives me a much better intuition of what's going on here. Okay. Little highlight sentence here. The key property of reflow is that it preserves the terminal distribution, right? It doesn't affect the marginal distribution, the final marginal distribution there, while straightening the particle trajectories and reducing the transport cost of the transport mapping. Okay. And this is kind of, here's another nice little picture of what's going on here, right? Where every single little pixel, right, is taking some meandering path to get to the, from noise to the final image. And here's your little ODE, right, which is kind of approximating that. And you can sample this ODE at different time steps t and kind of accumulate an approximation, or eventually you can get this straight trajectory, which is what they're going to do in this paper, where you just go from the start pixel to the end in the fastest, straightest possible path. And the straightness here, this is like obviously 2D, but it's not straightness in 2D. It's straightness in this higher dimensional space here, this RD, right? Okay, and how are you going to get that optimal mapping? It's just going to be a mean square objective. What does the mean square mean? Just this right here, right? You're squaring this here. You're squaring the ddt of x of t minus this ODE or flow model, right? And integrating that from 0 to 1. So this little script here basically just means integral, and 0 to 1 here refers to the time 0 and then time 1. And you're finding the v that minimizes this entire expression here, right? Where x0 and x1 are sampled from gamma. And what is gamma? Gamma is a coupling of... why is this weird? Gamma is a coupling of pi naught and pi 1, right? Where pi naught is your noise distribution and then pi 1 is your image distribution. X of t is phi, x0, x1 t is any time differentiable interpolation between x1 and x0. So let's make that yellow, right? This is an interpolation between 0, xt, or x. Here they're calling it xt and x0, but in the paper, x0 is the noise and x1 is the image. So it's flipped from this figure. So watch that because it's a little bit confusing. But here, these are all interpolations, right? These are all little interpolations between this and this. So that's the time differentiable interpolation. Time differentiable basically just means that you can take the derivative with respect to time. So here you can see dt, your partial derivative of this thing here, with respect to time. If you couldn't take the time derivative, then you couldn't calculate this. And if you couldn't calculate that, then you're basically fucked. So that's why it needs to be time differentiable. A simple example of gamma is the independent coupling pi naught cross x1. Here's your pi naught cross x1 there, right? Definition of coupling that they gave us here. X cross y, you have x cross y. You could think of it like, when you think of right-hand rule, right, you think of x, y, and then the cross product gives you some measure, but it's in a new dimension, right? And that's what's happening here, right? So you have x and y, and then you have the measure is now orthogonal to both of those. That's where that cross is, right? So your coupling gamma is just the cross between your noise distribution and your image distribution, which can be sampled empirically from unpaired object data, right? So what do they mean by that? So obviously you don't know what this coupling is, right? That coupling is extremely complicated because even the distribution of all images is extremely complicated, right? You can't write that down as a formula, right? But you can sample it. You can sample examples from that. You can say, okay, well, for this noise here, here's the image. For this noise here, here's the image. For this noise here, here's the image. So you could have a ton of samples from that. You can empirically just keep sampling because you have these huge data sets, right? And if you sample 100 times, that gives you a kind of good estimation of that. If you sample 1,000 times, it gives you better estimation. And as you keep increasing the size of the data set, you're going to get a closer and closer approximation as to this true coupling from pure noise to the actual image distribution. So as you increase the number of images in your data set, your approximation of pi 1, which is the distribution of images, gets closer and closer and closer and closer to the actual true distribution of images, which is some giant magical distribution that you could never actually write down because it's too weird, right? Different specific choices of the interpolation result in different algorithms. Commonly used denoising diffusion implicit model and the probability flow of ODEs correspond to this. With specific choices in the rectified flow, however, we do this. So This is just dt of xt equals x1 minus x0 right here. This is just straight, right? So here is your kind of like a piecewise, right? So xt, so here would be x0, here would be x1, here would be kind of intermediate steps here like this, but they're just going to basically do a one-shot straight, right? Which favors straight trajectories that play a crucial role as we discuss. Okay, straight flows yield fast generation. In practice, the ODE in one needs to be approximated by numerical solvers, right? And what is a numerical solver doing? A numerical solver is actually just going step by step. Let's go back to our thing. So what a numerical solver does is it basically, it does this gradual process for you, this Euler approximation where you're basically start from here, plug it into the ODE. What do I get for the derivative? Okay, take some small time step t, plug it in there. What do I get for the derivative? Okay, take that small time step t, plug it in there. What's the derivative? Okay, take a small time step t. So that's a numerical solver is just basically kind of like just plugging in numbers over and over again and trying, and you can basically say how small is this delta t, and if you want to use a very, 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 very small delta t, then that numerical solver is going to get you increasingly closer and closer and closer to the actual function. But obviously you have the kind of trade-off, cost accuracy trade-off here, where if your step size, which is here 1 over n, is too big, it's not going to be very accurate, but it's going to be very fast. If your step size is too small, it's going to take forever, right? You're going to have to simulate these n steps, but the approximation is going to be pretty good, right? So you have zt plus 1 over n. N is the step size. You're taking these small little steps of size 1 over n, and for all t in this. So you basically have some amount of n, and you have to pick what that value of n is. In fast simulation, it is desirable to learn ODEs that can be simulated accuracy and fast with a small n. So that's what we all aspire to, I suppose. This leads to ODEs whose trajectories are straight lines, which is kind of what they described up here, right? Ultimately, you want that straight line trajectory, right? You want that trajectory where every piece of rubble, every rock in that rubble pile knows exactly where it's going to end up in the castle, and this basically just moves in a straight line all the way to that final resting place. Or, in the analogy of pixels and image distributions, every single pixel in the pure noise distribution knows exactly where it's going to end up at the very end, and it just goes directly there in one step. Here you go, straight flow again. Euler method with even a single step yields perfect simulation. See figure 4. Straightening the ODE is an essential way for reducing the inference cost. Right. So if your ODE gives you a perfect guess and you just need to take one step, then that means you really only need to do one inference. One inference will give you the final image, and you can go straight from the noise all the way to the image. Straightening via reflow. Reflow is an iterative procedure to straighten trajectories of rectified flow without modifying the marginal distributions, right? And what do they mean here is that you don't want to, it can't mess with the final castle and the original rubble, right? So you could mess with the distribution itself, right? So one way to think about it is you could modify this distribution here, right? You could modify the pile of rubble such that the optimal transport is better for the castle, right? Or you could modify the castle such that the rubble is easier, right? So you can modify each of these marginal distributions here, but you don't want to do that, right? Because in our case, it's a pure Gaussian noise and then actual image distribution. So you don't really have the freedom to mess with those. So you can't modify those marginal distributions. So how are you going to iteratively straighten the trajectories for that flow? Hence allowing fast simulation. We have an ODE model, dxt equals vk xt dt. So here you see they just basically partial derivative. They just of this xt with respect to time. They just pulled that dt there, and they're basically saying this here. Velocity field v of k, right? So the velocity field is this here. This is not, it's not the exact same thing, but think of this. When you think of velocity field, just think about like pixels and the trajectories that those pixels can take, and there's basically a field of flow. There's like a flow over the time. Kth iteration of the reflow procedure is this, ODE vk. So here they're using their ODE solver for k steps, I guess. We obtain at t equals 1 when following the vk ODE starting from x naught. A reflow step turns vk into a new vector field, vk plus 1, that yields straighter ODEs while x1 new. So you can see here how basically what they're going to be doing is they're going to be iteratively improving this v of k. So this v of k here, right, which is basically they defined up here as the ODE for the flow between Z0 and Z1, right? This is what the at the very beginning, right, the path is kind of weird and meandering, and the ODE for that, if you were to kind of query it, would kind of change. You see that? How, like, if I were to sample right here and say, okay, well, what is the derivative right here? Well, it points down. What is the derivative right here? Well, it points sideways. What is the derivative here? Well, it points up. Versus here, right? What is the derivative here? It's the same. What is the derivative here? It's the same. What is the derivative here? It's like in this field or velocity field. What are they calling it again? Vector field. In this velocity vector field, every single vector along this trajectory points you in the exact direction of the final place. Versus here, it doesn't necessarily do that, right? This the vector here actually kind of points you there. So this vector field, not as good, not as clean as this vector field here. So that's what they're going to be doing with this reflow, is they want to move from this shittier version of VK to the better version of VK, right? The VK plus 1 that yields straighter ODEs, while, of course, making sure that the marginal distributions are not modified. So what does this actually look like? VK plus 1 is the V that minimizes with x naught sampled from pi naught, right? So pi naught is the noise, so you're sampling some noise from pi naught. Here you're integrating from 0 and 1. Here you have the squared difference between x1 minus x naught, where x1 minus x naught is literally just your image and your noise. So here's your final image, the difference between your final image and your final noise, and then the vector that should point you in that exact direction, right? So if the vector doesn't point you in that direction, then this is going to be big, and that's going to be larger, and you're trying to minimize this entire expected value here. With x1 equals ODE VK x naught, and xt equals tx1 plus 1 minus tx naught. Okay. VK plus 1 is learned using the same rectified flow objective, but with linear interpolation pairs constructed from the previous ODE. Okay, so they're kind of using pairs of x0 and x1 from the previous ODE, I guess. This is the sentence that we saw before. The distribution of ODE VK plus 1 and ODE VK, and you're feeding both of those the same x0, right, the same noise, coincides. Hence, VK plus 1 transforms from pi naught to pi 1 if VK does so. Okay, so they're saying since the marginal distributions are the same, therefore VK plus 1 should be giving you the same mapping as V of K. It's doing the same map from pi 0 to pi 1. The trajectories of ODE VK plus 1 tend to be straighter than that of ODE VK. This suggests that it requires smaller Euler steps n. So smaller Euler steps n here. Oh my god, this highlighting is gross. Just means smaller steps, right? Here you have 4 steps. Imagine 10 steps. Imagine 100 steps. Imagine 1,000 steps, right? And that's what your ODE numerical solver is doing. If V of K is a fixed point, then ODE must be exactly straight. Performance better than coupling in that it yields lower convex transport costs. That is the expected value of the cost. So there's some cost function here, C, that they've introduced here. So the cost is basically, in the analogy of the castle and the pile of rubble, the cost is just how many dudes had to sit there with the wheelbarrow and carrying every single stone from the pile of rubble to the castle. And if they had to carry every single stone a huge amount of times and over a larger path, that's going to be a higher cost. If they could just carry that one stone once with a much straighter path, that's going to be a lower cost, right? So there's some notion of a cost here, a cost to this kind of more meandering path from the noise to the image distribution versus the cost of the straight path from the noise to the image distribution. For all convex functions. C, this suggests that the new coupling might be easier for the network to learn. Yeah, and this is, I think, a little piece of insight here as well, where maybe the fact that it takes this kind of meandering path to get from the noise to the final image distribution is actually more difficult than the straight path, right? Maybe if it actually learned the straight path, maybe it would actually even be better than the kind of more meandering path. I don't know if I necessarily agree with this, because I think that it's probably using these kind of like intermediate points in some way, right? So when someone's like painting something, right? I don't know of any human painter that like basically paints the final color of every single like basically painting the final pixel, right? Generally, for example, they'll paint an oval for the face, and then they paint the eye on top of that, and then they maybe add the iris on top of the eye. So like if you think of every single patch of that painting, it's going from white, then maybe to black, then it's going to the skin color, then it's going to the whiteness of the eye, then the black color. So like as the painter is adding more and more detail, they're kind of like the trajectory of every single little patch within that painting is kind of meandering about, right? The actual pixel value of that exact area of the painting is changing because the person's kind of putting layers on top of layers on top of layers on top of layers, right? Versus like someone who could just like perfectly draw something by just going pixel by pixel and drawing the final color, right? So that's not what's going on here, but I do feel like there's something akin to that, right? There's something where the kind of the meandering path maybe results in the higher quality, right? In order to generate this exact part here, like having some of that intermediateness here maybe is better. So I don't know if I 100% agree with that. This new coupling is easier, but it's certainly faster. In text-to-image generation, the velocity field should additionally depend on an input text prompt T. Okay, so much how in the original diffusion model, you're removing this noise, and every single iterative removal of that noise is conditioned or dependent on, if you want to think of it that way, or influenced by is another way you could think about it. Much like that's conditioned on some text. In this case, this vector or velocity field V should also be dependent on some text. So you can see here how this velocity V, and this is the same exact equation from up here, but here you see V x t t, right? So the V is just x, t, and t, but here now V also has this big script t here, which is the text. So now it's the same V x t t, but it's conditioned on this text t, right? So they've just added the text t sampled from some distribution of text prompts t. So this is basically the same exact equation from up here, but now with the addition of text prompts and then conditioning that velocity field with that text prompt. Okay, D of t is a data set of text prompts, and ODE VK X naught conditioned on t. Okay, I think that's just basically the same thing. We set V1 to be the velocity field of a pre-trained probability flow ODE model. So they start from stable diffusion, and then they're going to basically go through this reflow step k times. So they're going to do k iterations of this reflow process to eventually get to what they hope is basically a straight trajectory for every single little pixel. My intuition is the early denoising steps are compositional, then later style. Yeah, every dream. That's what I think too. I think it's like I keep going. I was trying to explain this analogy, but it's like if you were to like time lapse of painter, right? Like so, let's go here. This random time lapse here, right? Like this person's doing this, but like look at this pixel here, right? So this pixel here is like this like kind of weird brown. But if I go earlier, it's like peach colored. So it goes from being peach colored to brown, and then she does more detail. So it's like generally the way that humans paint, it's like you're layering on top, and like the layers are useful for determining the next layer, right? So it's like you're kind of like each individual little pixel in this image is changing colors, right? It's like it's starting maybe lighter, and then it goes darker, and then it goes lighter, and then it goes darker, and then it goes lighter. So like you could say from an optimal transport, it's not optimal, right? Because it's taking this kind of meandering path in color or pixel space to get to the final color. Another way to think about it is that when we're building a castle from a pile of stones, it's not an optimal path at all, right? Generally, you take all the stones and you put them into like this prep area, and then you put them into a second prep area, and then you put them onto the scaffolding. So like the path that every little stone is taking is actually kind of not optimal at all. It's kind of taking all these weird meandering steps. So I think that meandering path has other benefits. So even though here they're saying, okay, well, just go directly to the final place, yes, that's going to be faster, but I think maybe you're losing a little bit of representational capacity there by doing that. Yeah. Exactly, Johnny. That's a good way to summarize it. We're learning the straight path by taking the maximum likelihood of the straight trajectory with the meandering ground truth prior. Exactly. And the prior is basically coming from sampling the stable diffusion with a bunch of data, right? So you're sampled empirically. So you're just taking a bunch of pictures and you're basically doing this with the stable diffusion model, the stable diffusion 1.5, and then they're saying, okay, here's the path that this little pixel took for this noise and this image using stable diffusion 1.5. Could we have taken a shorter path? And then they keep asking that question again. Could we have taken a shorter path? Could we have taken a shorter path? And they do that over and over and over again for k full steps of this kind of rectified flow process. Here they're calling it k rectified flow, and eventually you basically get this field vk plus 1, which will just take you directly there. Distilling, this is basically just these equations, but written in kind of like a pseudocode format. Pre-trained stable diffusion model, VSD equals V1, a data set of text prompts, so VSD is the stable diffusion path that it takes. Data set of text prompts, D of T. 4K less than or equal to a user-defined upper bound. Do initialize VK from VK, VK plus 1 from VK. Train VK plus 1 by minimizing the objective 6, where the objective is basically the kind of total path, right? The more kind of weirdness, the higher the cost. So you're going to want to minimize the total cost. Another way of thinking about that is basically just this here. You're minimizing the integral there. The trained VK is called a blah, 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 okay, and then distilling text conditional K rectified flow for one-step generation. Okay, so now this is just training the rectified text conditional rectified flow, and then they distill it for one step. So in this algorithm 1, they're getting this vector field, and they're making it more and more straight, but it's still multi-step, right? It's still the same number of steps as this, right? It's just that every single step is a little bit more straight. You're kind of straightening out the path that it takes, but it's still just the same amount of steps. So now, in order to make it one step, you're going to have to do this distillation, right? Where you're going to go from multi-step to one step. But they went through this rectified flow where they were rectifying the flow. So whereas previously the stable diffusion model, each of these green arrows was a little bit more meandering, not necessarily in the same direction, they've turned it into this kind of new version, right? This VK plus 1, which is more straight. It's more rectified. And now they can distill that into just one step, right? And because it's more straight, doing it in one step, you're not going to end up in a weird place. You're going to end up pretty much exactly where you want it to end up. So that's kind of like the two-part there. Train VK by minimizing the objective can be generated beforehand. Okay, so this is kind of the two-step process. First, you rectify this velocity field, this trajectories, right? This flow, and then you distill it. You distill that model down so that it can do it in only one step. Okay. And that's what this distillation is here. So theoretically, it requires an infinite number of reflow steps to obtain ODEs with exactly straight trajectories. Okay, so it's not even necessarily straight. However, it is not practical to reflow too many steps due to the high computational cost and the accumulation of optimization and statistical error. Fortunately, it was observed that the trajectories become nearly, even though not exactly straight. Boo, come say hi. With even just one or two steps. With such approximation, one approach to boost the performance of a one-step model is via distillation. Here's your distillation. Here we learn a single Euler step to compress the mapping flow by minimizing the differentiable similarity loss between images. Come here, you're getting shown. You're getting shown to the stream. You have anything to say? Okay. We adopt the learned perceptual image patch similarity loss, so LPIPS. LPIPS is actually very similar to, if you guys remember Frechet inception distance, which I explained earlier in the stream, is basically the distance between the features of images as they're seen by an inception v3, which is a pretty old model. LPIPS is basically the same shit, except it's a little bit more complicated. You're feeding images through an AlexNet, which is also a very old convolutional neural network, and then you're kind of looking at the intermediate feature representations here, and then doing a kind of a similar similarity score. And LPIPS here, you can see how you can actually change the net type. So here, the AlexNet means that the network that you're using to compare the features in, you can change it. But I think they just use the AlexNet, which is why I feel like they could have used something better here. It's like it's not even like a Frechet inception distance where you're just using that to show results, but here the LPIPS is being used directly for distillation. So if they use an AlexNet based LPIPS for this, I feel like they're leaving a bunch on the table. They should have used a better I don't know what other options exist. VGG, Alex, Squeeze, all of these are kind of old. SqueezeNet, VGGNet, these are kind of gross. We need a better LPIPS and we need a better Frechet inception distance, especially if you're using it as a loss here. And the way that they're using it here as a loss is for this distillation process. Learning one-step model with distillation avoids adversarial training or special invertible neural networks. Okay. It is essential to use reflow to get good coupling before applying distillation. It is important to note the difference between distillation and reflow, right? Two different processes. The reflow is just making those paths straighter, and then the distillation is training a smaller version of the model such that it can do it in one step. While distillation tries to honestly approximate the mapping from X0 to ODE, reflow yields a new mapping that can be more regular and smooth due to lower convex transportation costs. In practice, we find that it is essential to apply reflow to make the mapping ODE sufficiently regular and smooth before applying distillation. Right, so this is kind of what we were seeing, where it's basically this two-step process. The reflow is just for the purposes of making that vector, that velocity field kind of more straight, and then the distillation makes it one step. So you need to do the reflow before you do the distillation. Classifier free guidance velocity field for rectified flow. So you have your velocity field, right, which is what your rectified flow is trying to make straight, and that rectified flow, or that velocity field, is guided by some text, right? So we saw how the velocity field here is conditional on this text prompt T, right? So classifier free guidance, this is kind of a whole other rabbit hole, but basically classifier free guidance was this idea where you can condition on the text. So here you see conditioned on text and then conditioned on null, so conditioned on nothing. So what is the velocity field when conditioned on this text, and what is the velocity field when conditioned on nothing? And then you can take basically the alpha 1 minus alpha difference between those, and you get a slightly better, I guess, velocity field. Generally, when people talk about classifier-free guidance, they'll refer to like a very specific number, which you can basically trade off alpha here, which trades off the sample diversity and generation quality. I think the better way to think about it is that it's basically what's coming out of here, right? So we're feeding your text into this text encoder, and then that's being used to condition this denoiser. But imagine if, like, sometimes you cut off this little connection here. So sometimes what's going into here is nothing, right? It's null, it's empty. So it's just removing the noise with no conditioning. And then sometimes you leave it. So sometimes it actually uses the conditioning. So being able to trade off between, okay, how much conditioning are you adding versus no conditioning? And that's what's here. So this is no conditioning. And then this is conditioning with the text. And kind of the in-between of those two gives you that ability to kind of trade off between sample diversity. So if you condition on nothing, it's going to be more diverse, versus if you kind of make it very, very specific to that text, it's going to be kind of maybe too narrow, right? So kind of somewhere in between is kind of that magic spot. When alpha equals 1, V alpha reduces back to the original velocity field. Okay, so if alpha equals 1, then this 1 minus 1 becomes 0, which means this entire term here becomes 0, and your velocity field is just simply the text-conditioned velocity field from before. Okay, preliminary observations on Stable Diffusion 1.4. So they do all of this with Stable Diffusion 1.4. I really wish they would have used Stable Diffusion 2 and even Stable Diffusion XL. There's improvements there. Stable Diffusion 1.4 might even have the bug that we found in a previous paper that we were looking at. We didn't find it, but we read a paper where someone found a bug. So I wish they would have used a more recent version, but I guess, you got to do what you got to do. Goal of experiments is to examine whether straightforward can be effective for learning a one-step model, examine whether text condition reflow can enhance the performance of distillation. Our experiment concludes that reflow significantly eases the learning process of distillation, and distillation after reflow successfully produces a one-step process. So maybe kind of what they're suggesting here is that whenever people were doing distillation before, the path that you were going from noise all the way to the image distribution was meandering, so that whenever you were trying to distill it down, it was hard, right? That vector field that you're basically trying to distill is complicated, so distilling it is not going to be as good as if you first straighten it, which is what they're doing with this reflow, and then distill it. So that's kind of what they're arguing for here. And of course they have the experiments to show that it works. We use the pre-trained Stable Diffusion 1.4 in the open source repository, since otherwise the convergence is unbearably slow. I like that. In our experiment, we set DT to be a subset of text prompts from Leon to be English, pre-processed by the same filtering as Stable Diffusion, implemented as the pre-trained Stable Diffusion with 25 steps, so this starting from a 25 step. Fixed guidance scale of 6.0. The guidance scale is this part here. Let's actually do blue for that. I think blue is what we use for numbers. Let me make this blue. So here's the guidance scale would be this, alpha. We set the similarity loss for distillation to be the LPIPS loss. Again, I wish they would have used a better loss here. I just don't like LPIPS and FID. Neural network structure for both reflow and distillation are kept to the SD UNet. Here they're referring to the UNet in Stable Diffusion, this part here, right? Your little UNet, which basically takes your little latent and then predicts the noise, and then you can remove that noise. Actually, SDXL is not a good model for the community because it is not anime model, and many anime leverage GPU devices. Huh. So you're saying SDXL has officially passed, this is a question from Eugene, you're saying that because it's too big, people can't use it. Yeah, I kind of agree with that. I had a similar kind of, I think I made that same point when we were reading the SDXL, where at some point, you're going to make a model that's too big for most people who have GPUs, and at that point, then you're going to lose a huge chunk of the people who can even use it, right? So if you're Stability AI and you want to create open source models that you want a lot of people to use, you kind of want to make sure those models don't use a lot of VRAM, a lot of GPU memory, because if they use too much GPU memory, nobody's going to use them, and then at that point, what are you even doing, right? But I don't know, maybe a little side tangent. I don't think Stable Diffusion is going to be open source for much longer. Right? So Stable Diffusion, Stability AI, they recently released an audio model, right? So stable audio, but there's no paper and there's no model. So the only thing they released is like, hey, you can pay us money to do this. So if you go to Stable Audio, you can pay them money. So like here, let's see try it out for free. No, I don't want this. I want learn more. I don't know where it is, but basically it's kind of like Midjourney, where it's like you pay a certain amount of money for total amount of inference steps, but they're not actually kind of really releasing this. They kind of give you this kind of vague idea here of like, oh, this is kind of what we did, and like blah blah blah, we trained it, but where is it, dude? Release the model so that we can use it. But I think it's just realistically, if you're a startup, you have to have your own proprietary model, and you have to basically put it behind an API and then have an API where usage is basically paid. So I don't know. I think Stability AI, they started off with this idea of like, we're going to be open source and everything's open source. And then now suddenly they're like, holy shit, we have bills to pay. We have to pay all this money, pay all these researchers. We're never going to be able to do that if we're all open source. So therefore we have to start paying, and we have to start hiding our models. So I don't know. We might already be past the age of free open source models that are available for you to kind of do what you want with them. I don't know, tangent over here. They have a batch size of 32, 8 A100 GPUs, so they have an A100 GPU server rack. For training with AtomW Optimizer, kind of basic stuff here, we adopt exponential moving average with a ratio of 0.99. This is EMA, so you can see all these, this is literally the actual script that they are using. They don't actually release it on their repo. So far we don't have anything in this repo, but they say that they use this training script. So all they probably did was just basically add to this training script. You can see here, here's the EMA model, the exponential moving average. You have all your different favorite pieces here. You have your UNet, you have your DDPM schedulizer, you have your KL or auto encoder, right, which is your encoder and decoder. What do we got here? Direct distillation fails. Our investigation starts from directly distilling the velocity field of stable diffusion. Okay, so basically they try to just do progressive distillation just directly to one shot without doing this rectification process. And that's what they're doing here. And I think without even reading the section, I'm kind of already learning that it's basically going to fail. Okay, so if you try to distill stable diffusion 1.4 directly, you have a much higher FID, right? Higher FID means higher distance, which means that it's not quite there. So here's what you get qualitatively. That's easier to see, right? I don't know what the Frechet inception distance of 40 is, but I can tell you that this image looks looks not like this image, and this image looks like this image. So here, this is where they do this rectified flow process. They only do it for 2 steps, which is actually interesting, right? So 2 rectified flow means that they do for k equals 2 iterations, right, of their little algorithms here. They do 2 steps of this k rectified flow here, where they're straightening out that velocity field, and then they do the distillation, and you can see how it's significantly more true to the original stable diffusion 1.4 velocity field. They release some things first on close. Guess we'll see if SD audio gets released. Yeah, I don't know. It's kind of sad because this entire YouTube channel depends on having open source papers and open source models and being able to do stuff, but I feel like the way that just the amount of money and competition in the AI space means that people are becoming more secretive. People are becoming less likely to publish models, less likely to release models. So I feel like a year or 2 from now, I might not even be able to do what I'm doing right now. There might not even be papers anymore, right? Like, if people stop releasing papers, what the hell am I going to do? You know, it might be the kind of thing where it's kind of like, you know, like if you're into aeronautic engineering or something like that, right, and you love all about like airplanes and stuff like that, like there's no papers on that. You know, all that shit is secret. You know, Lockheed Martin doesn't release their stuff dealing with fighter jets and the material science and like all the cool stuff that they're doing. So you couldn't have a YouTube channel where you review the public papers about the material science behind fighter jets because all of that is secret. And I feel like that same thing is going to happen to AI, where unfortunately there was like a golden period, which we're kind of at the end here, where people were releasing everything that they were doing, and you could go and you can review it like I'm doing here. But I feel like a year or 2 from now, it's not going to be the case anymore. People are not going to release what they're doing, and unless you're literally working at OpenAI, you're not going to know what they're doing, and you're not going to be able to do this kind of stream. So enjoy it while it lasts, guys, because this isn't going to last forever. We conduct a grid search on learning rate, weight decay to limit our computational resources. So here they're talking about the learning rate that they use for the distillation. They try a couple different learning rates. They try a couple weight decay coefficients here. Blah, blah, blah. Compute the Frechet inception distance. We show the model the lowest FID. Model distilled from 2 rectified flow has a lower FID and a smaller gap with a teacher model. Again, so distillation, you're training a student from the teacher, right? In this case, they're training a student which does it in 1 step from the teacher which does it in 25 steps, right? So the teacher is stable diffusion 1.4, the student is the distilled version, and here you see the difference from rectifying the flow beforehand. So still a little bit of difference, but you can see here how it's way better. All 9 models converge. However, the learned 1-step generative model is still far from satisfying. There's a huge gap between SD and SD plus distill. It's difficult for the student to imitate the teacher. Direct distillation from SD is a tough learning problem for a student 1-step model, hard to mitigate by simply tuning the hyperparameters. Okay. Reflow improves cooling and eases distillation. I think this is another mistake. I think they probably meant coupling here. For a fair comparison with distillation, we trained V2 for 50,000 steps with the weights initialized from pre-trained SD, then performed distillation for another 50,000 training steps. Okay, so they're doing some kind of like more complicated crap here. Distilling, guidance scale. Seems like they're trying a lot of different hyperparameters here. So here's a guidance scale is a hyperparameter. The total amount of steps that you use for this rectified flow is a hyperparameter. The learning rate for the distillation is a hyperparameter. The weight decay for the distillation is a hyperparameter. And that's kind of what they're suggesting here, where they wanted to make sure that whenever they get these results, it's not just a weird set of hyperparameters. So they're trying a very broad, they're casting a very broad net. Here, for example, you see a grid search. So grid search is something that you generally don't want to do for hyperparameters because it means that you're literally trying every single permutation of hyperparameters. It's the most expensive hyperparameter search process. Generally, you want to do something a little bit better than that. You know, even random is better than grid search sometimes. I know that's kind of like a spicy take, but they wanted to make sure. So you can see them just trying all kinds of weird hyperparameter here. Similar FID indicates that reflow can be used to learn generative ODEs with comparable performance. 2 rectified flow refines the coupling between noise and the image and eases the learning process for the student model when distillation. Yeah, that's kind of what we've been seeing this entire paper. The gap between 2 rectified flow plus distill and 2 rectified flow is much smaller than SD distill and SD. The image generated from 2 rectified flow shares great resemblance with the original generation, showing that it is easier for the student to imitate. 2 rectified flow is a better teacher model to distill a student model than the original SD. But then this goes back to kind of what we were saying, where, yeah, the rectified flow makes it easier to distill, but maybe by rectifying the flow, you're losing some of the capacity of the original teacher model, right? This is kind of now the 50th time I bring it up, but there's something to that, right? I feel like there's something to that weird path that you take that probably allows you to kind of generate a slightly higher quality, right? Because maybe the weird path, like maybe it has like a slightly larger ear, and then because it's a slightly larger ear, it makes it better for refining the final ear, right? So like, I just feel like there's something to the kind of weird flow of the stable diffusion model that if you straighten out that flow, you're losing something. I don't know exactly how to quantify or describe what that something is, but it's something. You know, you're losing a little bit of that magic. Okay, so here they're comparing FID 5K. This is distance for an inception V3 model, and then clip is basically the same thing, but now you're using a more modern clip model. So it's the same thing. You're kind of like doing the distance in clip space. So a bigger clip distance means that it's more far apart. So lower FID is better, and I think lower clip is also better. Inference time is measured on an NVIDIA A100, batch size of 1. PyTorch 2.0. Ooh! PyTorch 2.0? What the fuck? Why are they using Stable Diffusion 1.4 with PyTorch 2.0? Huh. PyTorch 2.0 is faster, but it's kind of a pain right now because a lot of the stuff that you use is not, was not written with PyTorch 2.0, so like you have all these kind of dependency and compatibility issues, but it's kind of weird that they were able to use that. Measured from blah, blah, blah. Okay, so 2-step versus 4-step. 2 rectified flow, 3 rectified flow. This might be interesting here. So 2 rectified flow versus 3 rectified flow. Huh. So, I mean, it does seem like the extra step of this rectification process does actually give you a benefit there. So, I don't know why they did all those examples with 2. They should have done 3. Right? Seems like the 3 rectified flow works better. Maybe not. Like, look at this. 24 to 26. And here's the kind of base comparison. 25 steps of Stable Diffusion 1.4 takes about 0.88 seconds versus 1 step of this 2 rectified flow distilled network takes about 0.9 seconds. We provide additional quantitative... Ooh, I just fucked up big time right there. Let's go back down. Where were we? Right here? I think we were right here. Quantitative results, further analysis, expanding the network size. We consider 2 network structures, UNet, stacked UNet. Compared with 2-step inference, stacked UNet reduces the inference time from 0.12 to 0.13, removing a set of unnecessary modules. Stacked UNet is more powerful than UNet, which allows it to achieve better 1-step performance after distillation. Okay, so here they're referring to the teacher model is the UNet from Stable Diffusion 1.4, and the student model is the one that they're distilling to. But in this case, it actually seems like the distilled UNet is even bigger. I'm guessing stacked UNet means they probably have 2 of these UNets back to back. So in this case, it's a little bit weird, but they distill a UNet which takes 20 steps, or which is smaller but takes 20 steps, and they distill it into a UNet that's bigger, a stacked UNet, but only does it in 1 step. So it's kind of like a little bit of weirdness there, but it's still faster because it does it in 1 step, even if it's a bigger model. According to the equation, the reflow procedure can be repeated for multiple times, so they get the 3 reflow versus 2 reflow. Rectified flow minimizes distilled version, generating new pairs and distilling for another 50,000. Okay. Because our rectified flows are fine-tuned from publicly available pre-trained models, the training cost is negligible compared to other large-scale text-to-image models. Yeah, you don't need to train it from scratch, right? You're starting from the Stable Diffusion 1.4. On our platform, the training with a batch size 4 in UNet, 1 A100 GPU day can process 100,000 iterations. When generating pairs, their batch size of 16, 1 A100, blah, blah, blah. Okay, so earlier, right, in the abstract, they said that they basically had a training budget of like something like 190 A100 GPU days. But part of that is their huge hyperparameter sweep, right? So they sweeped over a large hyperparameter space, which is actually why their training budget was so big. But actually, if you were to train this just once on just 1 set of hyperparameters, you could literally do this on 1 A100 GPU. So that's kind of interesting. And they compare it to, for example, the training cost for SD 1.4 is 162 or 6,050 A100 GPU days. It's fucking monstrous. StyleGAN T is 1,700 A100 GPU days. GigaGAN is 4,783 A100 GPU days. Jesus. A lower bound estimation of training the 1-step SD and progressive distillation is 108 GPU days. Damn. And this is why Stable Diffusion and Stability AI needs to figure out a way to make money, because this right here, that's a one-time cost, dude. They're never going to get that money back, right? This 6,000 A100 GPU days, that was the cost for training 1.4, but now that they trained 2.0, all this cost right here is in the bucket, in the drain. So that's why these startups that are training foundational models have to figure out a way to monetize quickly, because training these things is very expensive. And then as soon as you train the newer version, all the training you did for the previous version is basically worthless. Our first experiment follows evaluation protocol. Measure the FID score and the clip score using the VIT G14 clip model. So this is a much better, more modern model than the Frichet Inception, which is based on the Inception. So look at that. At least we're using a vision transformer instead of a ConvNet. So that's an improvement. Record the average running time. For comparison, we use the inference time. Rectified flow. Okay, here they're basically just putting this table but in text form. Here they're comparing their UNet versus the stacked UNet, right? So they're distilling either into the same network architecture, which is the UNet, or they're distilling into something that's this stacked UNet. So you can see how the stacked UNet takes a little bit longer, 0.12 seconds versus 0.09 seconds. It's a little bit bigger, but it's going to be better. It's certainly going to be faster than the original one because this one does it in 25 steps, right? So you can see here 25 steps with the UNet, 2.9 seconds. One step with the UNet, 0.9 seconds, 0.09. One step with the stacked UNet, 0.12 seconds. But this is the difference here. This is kind of weird. The stacked UNet actually performs worse than the UNet if you're just distilling, but if you first rectify it, then the stacked UNet is way better. Why is this the same? The fuck? Why is the stacked UNet the same size? That's weird. Let's see. They said they had it in the appendices. Here we have some pictures. Look at these pics. Beautiful pics. Here we go. Stacked UNet. So here's your normal little UNet, right? And there's that U shape. Inference time 0.04. And then the stacked UNet. But they said it's the same number of parameters. So what is going on here? Blocks with the same color share weights. Okay, so it's basically the same UNet but twice. Okay, so the number of parameters stays the same because it's the same parameters. They just kind of like back to back put them like this. Okay, that's a little weird, but sure. It seems to perform better for them. What else? I'm kind of running out of time here. That's why I'm kind of trying to be a little faster here. Straightening effects of reflow. We empirically examine the properties of reflow in text image generation. To quantitatively measure the straightness, we use the deviation of the velocity along the trajectory following this. Okay, so here you have the pixel values. Here's the meandering path that we keep talking about in the original Stable Diffusion, which is taking 20 steps from time step 0 to 1, or from time 0 to 1. And then the rectified flow, which does it in one step, right? This is after the rectification process, 2 steps of that, and you can see how much straighter those paths are. There's still a little bit of kind of weirdness here. You see that? You see there's a little bit of a little, it's not exactly straight, but it's more straight. Okay, so they have this kind of measure of straightness. So S of Z is straighter trajectories, and if S of Z was 0, that means they're perfectly straight. And here you have a log chart of that S of 0, and you can see how original Stable Diffusion, not straight at all, right? And then kind of the, once you had this rectification process, the S of Z, which is this metric that kind of tells you how straight the trajectories are, you can see how it gets much better, but then 3 gives you only a little bit, and then 4 probably is even less important, so 2 is really kind of the sweet spot there. Towards better one step, scaling up on Stable Diffusion 1.5. Preliminary results demonstrate the advantages of adopting the reflow procedure. However, since only 24 A100 GPU days are spent in training, it is highly possible that the performance can be further boosted with more resources. Therefore, we expand the training time with a larger batch size to examine if scaling up has a positive impact on the result. The answer is affirmative. Here you go, guys. With 199 A100 GPU days, we obtain the first one-step SD that generates high-quality images on par with state-of-the-art GANs, StyleGAN, and StyleGAN T. So here you have qualitative examples of 2 rectified flow versus 3, 25 steps, 1 step. I don't know what the fuck I'm looking at here. N is the number of inference steps. If an ODE trajectory is straight enough, we see that N equals 25 and N equals 1 yields similar images. Okay. All the distilled models use the stacked U-net, so all of these are using the stacked U-net. The trajectory of stable diffusion is curved since n equals 1 leads to meaningless noises. Okay, so because the stable diffusion trajectory is curved, if you were just to do it in one step without the distillation, it's just going to be one step. It's just going to kind of look like noise. Distillation from stable diffusion results in blurry, low-quality images. That's what they're saying here. If you just distill straight, but once you rectify and then you distill, then you get something that's quite close. Okay. Implementation details. We switch to stable diffusion 1.5. Keep the same text for the conditioning on the text. They decrease the guidance scale a little bit. Expand the batch size. So you see here now they're using 32. So I think they have a batch size of 4 for every A100. Every A100 can take 4 images, and then they have a server rack with 8 A100s, which means that your total batch size is 32 for the entire compute node, I guess. Train the model using the reflow objective. Batch size of 64. Batch size of 1024. Shit. Dude, these guys are GPU rich. We mix time equals 0, fine tune it with a batch size of 1024. Okay, we switch to a similarity loss, then continue to train the model with a distillation objective for another 1800 iterations. The final model is 2 rectified flow plus distill. We name it InstaFlow 0.9b. Okay, so this is the final model that I guess they're probably, hopefully, going to release in this GitHub repo. But, yeah, I mean, you don't know. I don't know why they're not releasing it. But it basically went through 2 stages of reflow and then 2 stages of distillation. Damn, you guys are going ham here with the questions. I'm sorry. Slight reduction. Most GPU computers just research. Probably lots more GPU time thrown away constantly. They're just reporting specific generic. Yeah. The specific genetic line. That's kind of interesting. I've never heard of a model being referred to as a genetic line. We'll have to rewatch this video. It's a lot. Yeah, I feel like the concept is actually quite simple. It's just that the way that this is written is a little bit confusing. They put a lot of extra numbers here. You know, like, you don't really need to tell me, like, the total number of iterations. I'm glad they tell me all these, like, very specific details, but the main concept is pretty simple. It's basically just this figure here. It's just stable diffusion, the paths that it takes from the pure noise into the images is curvy and weird and doesn't get to the final place. They have this rectification process based on optimal transport. That rectification process makes it more straight, which means that you can then distill a model that does in one step. It's a relatively simple idea. It's just the paper is kind of verbose and gives you a lot of unnecessary details, but okay. We're getting to the end here. Total training cost, comparison of FID, large neural networks for one step. Expanding the model size is a key step. To this end, we adopt a stacked U-net and abandon the parameter sharing strategy. Okay, so, and this is also confusing because now, right, we were saying, okay, well, how do they have a stacked U-net that has the same number of parameters? And we looked at the appendix, and the appendix said, oh, the reason that you can have a stacked U-net with the same number of parameters is because we reuse the parameters. And I'm like, okay. And then literally, like, a page later, they're like, we're actually going to abandon the parameter sharing strategy, so now we're going to have a stacked U-net, but it's actually going to be roughly twice the number of parameters as the smaller U-net, which is 0.9, which is almost twice as large. Starting from the 2 rectified flow plus distill stacked U-net is trained on the following distillation step. Initialize from steps. We fix the time t, fine tune it. Okay, so this is basically the same thing here, except now they're using this larger stacked U-net, and then that's how you get InstaFlow 1.7b. And what is the difference between InstaFlow 1.7b and InstaFlow 0.9b? This is fucking meaningless. What? totally not worth it. Look at that. InstaFlow 0.9b, inference time of 0.9 seconds, FID of 23. InstaFlow 1.7b, almost twice as big. Larger inference time, of course, because it's bigger. But look at that. It's like pretty much identical FID and clip scores. So I don't know if this larger InstaFlow 1.7b is worth it. Made the following. The two Rectified did not fully converge. Distillation showed faster convergence. LPIPs had an immediate impact on enhancing the visual quality of the one-step model. Further improvements can be achieved. Two-step progressive distillation needs similar inference time. Two-step PD minimizes distillation loss at t equals 0.5, which may be unnecessary for one-step distillation. So two-step PD kind of comes from the original PD or progressive distillation paper where they have the amount of steps every time. So here you go from 4 to 2 to 1. So two-step PD means that your two steps are one step takes you to t 0.5 and then the other step takes you to t equals 0. They evaluate on MS Coco, and MS Coco is supposedly representative of a natural image distribution, aka an image distribution that you would expect out there in the natural world. Here they're comparing to a bunch of other generative models. You have ImageGen, which is a diffusion model generating images of size 256 by 256. Takes about 9 seconds, has a total of 3 billion parameters, and gives you an inception score of, or Fréchet inception distance of 7.27. Compare that to InstaFlow here, which is a diffusion model. I don't know why they didn't. It is a diffusion model. It's a one-step diffusion model. Higher resolution, much smaller inference time, less parameters, pretty close. And then compare that to a GAN, so a generative adversarial network here. That's a GAN, 512 resolution, takes about 0.13 seconds. Again, GANs only have one inference, or one feed-forward inference, so that's why the time is comparable here. 1 billion parameters, roughly the same amount of parameters, lower score. So I don't know, it's about on par with a GAN basically. Few step rectified flow has a straighter trajectory. Inference steps are 1, 2, 4, 8. 2 rectified flow. Guidance scale. It is widely known that guidance scale is an important hyperparameter when using stable diffusion. Why are they doing hyper-hyphenated parameter here? More typos. By changing the guidance scale, the user can change semantic alignment and generation quality. We investigate the influence of the guidance scale for 2 rectified flow. So they were changing this constantly. Like in the experiment section that we were just looking at, it seems like they messed with this guidance scale a lot. So let's see if they learned anything about it. While training is similar, there are 2 key differences. Even when alpha equals 1, the generated images always have decent quality since we perform reflow. It is possible to avoid classifier-free guidance using inference to save GPU memory. And why does avoiding classifier-free guidance save GPU memory? Because you don't have to condition with and without it. So if you're using classifier-free guidance, you have to run it once with the text conditioning going in, and then run it once with no text conditioning going in, and then you kind of trade off between those. But if you don't use the classifier-free guidance, you basically save yourself that cost of having to run it null and then having to run it with the text. So changing the guidance scale does not bring drastic changes. It only perturbs the details and the tone. Okay, so even though they messed with it a lot, they kind of don't have any interesting intuition or things to share with us. Basically, they seem to like say, yeah, it changes stuff, but we don't really know exactly what the fuck it's doing. So guidance scale remains a mystery. Here you have more pictures of Corgi. These are not super high quality, but again, they're comparing to, you have to compare to Stable Diffusion 1.5, so compare that to that, you know. Here's a 4K high resolution of a Avatar Pandora guy. Learned latent spaces of generative models have intriguing properties. By properly exploiting their latent structure, prior works succeed in image editing. Semantic control. The latent spaces of one-step generators are usually easier to analyze than the multi-step diffusion models. Okay, maybe. One advantage is that our gives a multi-step continuous flow in the corresponding one-step model simultaneously. The latent spaces of our distilled one-step models align with the two rectified flow. Therefore, the one-step models can be good surrogates to understand and leverage the latent spaces of continuous flow, since the latter one is higher generation quality. Okay, so the latent space still is there. So what they're referring to there is that, like, if you wanted to study this latent space here, right, and study how this latent space changes as you're kind of adding and removing the noise, they're saying that their rectified flow is a good surrogate, aka it's kind of like a one-to-one with the original latent space. So if you wanted to study it, you could look at that. Number of inference steps, clip scores. It's kind of just the same data over and over again. Okay, it's 10 minutes left. Gotta go fast. Random noise. One-step model. This is 512 by 512. This is 256 by 256. Fast preview. Our potential use case with one-steps is to serve as previewers. Okay. So you could generate a kind of a quick preview and then determine whether or not you want to keep going with that. Large-scale text can work in a cascaded manner. The user can choose one image from several low-resolution images, and then an expensive super-resolution model expands the chosen low-resolution image to a high resolution. It's kind of what Midjourney does, right? Where you basically, it generates smaller images, and then if you want, you upscale them just to save on compute and make things faster. Hence, a fast previewer can accelerate under the same computational budget. We verify the idea with the XDXL refiner. This is kind of the picture that they showed at the very beginning of the paper. InstaFlow 0.9, 1.7. Okay, cool. Best is yet to come. Okay, so I guess this is the conclusion section here. The recurrent nature of diffusion models. So recurrent nature of diffusion models. Why are diffusion models recurrent? Because basically you need the previous step to get to the next step, right? It's recurrent. It's auto-regressive is another way, I guess, of thinking about that. Hinders their deployment on edge devices. So here they're saying you can't do it on a cell phone because you need to do like 20 steps. But I don't think that's necessarily due to the recurrent nature. I think that's literally just due to the memory cost, right? The reason we don't have diffusion models on our cell phone is because the amount of memory on a cell phone chip is not high enough. It's totally, yes, the recurrent nature means that you would have to sit there and wait longer, but we don't even have the memory yet. So we demonstrate that a powerful one-step can be obtained from a pre-trained stable diffusion using the text condition rectified flow. We propose several promising future directions. Okay, improving one step. This is only a fraction. By scaling up the data set, we believe that the performance of one step will improve significantly. SDXL can be leveraged as a teacher. Yeah, so I would have used SDXL. That seems like obvious. One-step control net. Applying our pipeline to train control net, it is possible to get a one-step control net that's capable of generating controllable contents within milliseconds. Yeah, so the same way that here you're rectifying the flow that is text conditioned, you can rectify a flow that is control net conditioned, right? So control net, you can think of basically here, all they showed was for text, but you could pass all kinds of other shit in here, right? You could pass edge maps, segmentation maps, depth images, pose images. So the world is your oyster in terms of what you want to add as conditions. Fine-tune SD with a straining objective and a LoRa. Okay. Users can customize pre-trained SD to generate specific contents. However, as the one-step models have substantial difference from traditional diffusion, determining the objective for fine-tuning these one-step models remains a subject that requires further investigation. Yeah, I guess maybe what they're talking about here is the objective, like the LPIPs. Like that's, I'm still cringing from that LPIPs. It's widely acknowledged in the research that the unit plays a critical role. The advancement of creating one-steps, several intriguing directions, exploring alternative one-steps such as GANs could potentially surpass the UNet, leveraging techniques like pruning, quantization, and other approaches for building efficient neural networks to make one-step generation more computationally affordable. Okay. We're about to end here, but it seems pretty cool. Let me take a sip of this coffee, then we'll go back to the top and we'll summarize this paper. Maximum likelihood is faster but less accurate than full-blown Bayesian inference is the takeaway. I don't know. I'm not cool enough to to know exactly what you mean there, John. Okay. So today we read this paper called InstaFlow. This was a paper that was recommended by some of our viewers on the Discord channel, and you're welcome to recommend channels on that or papers on that if you're interested. It was also on the Hugging Face papers list, and also Papers with Code, a couple other different sources. So I figured if a bunch of people are talking about it, we should look at it. This is paper coming out of University of Texas in Austin and Helixon Research, which is some kind of weird biotech startup. Diffusion is used for protein problems, and actually we have a viewer on our Discord that is doing something cool with diffusion. So if you're from Helixon Research and you're interested in diffusion and protein, check out our Discord because we got people interested in that. Most of this research comes from a thread coming from Qiang Liu, this guy here. He basically has previous work that also deals with this rectified flow idea. Rectified flow comes from this literature of optimal transport. The whole process of optimal transport comes from some original 17th century French dude who basically wanted to figure out the optimal way of transporting every single stone in a quarry to build a castle. We have, of course, transferred that, and now the way that we think of that is basically two probability distributions. What is the optimal transport of mass from one probability distribution, one marginal probability distribution to the other marginal probability distribution, and there's kind of like a whole rich literature of optimal transport. Of course, we're doing it in this paper, not between a pile of stones and a castle, but we're doing it between a noise distribution and a image distribution. So in this paper, they take a Stable Diffusion 1.4, I think, and they basically do a two-step process, which turns it from a normal latent diffusion model like this that basically just takes 25 steps, I think, in their example, to produce the image, and they turn it into this model here, a distilled version of the Stable Diffusion model that does it in one step. So you can see here significantly faster inference time. The whole point of this is to try to get to the same level of quality, but in one step rather than n steps. Let's see. Here's a nice little picture. So the trajectories that every element of, or every pixel you can think of, takes from the beginning noise all the way to the final image is kind of curvy and meandering, and they want to make it straight. And I really like this figure here. This one here in the paper. Figure 6 is, I think, the best example, where in the original Stable Diffusion, right, you're doing 25 steps, and the reason you need to do those 25 steps is because some of the paths that the pixels take is not, they kind of meander around, right? Versus once you go through this rectification process or this reflow process, you turn these paths into straight. Basically what that boils down to is you're basically adding this cost constraint to this velocity flow, or what do they call it? Velocity field. And then you're trying to make this velocity field increasingly more and more straight. And here's the actual minimization objective that they use for that. My brain is starting to melt. So sorry if I'm kind of like tongue twisting my words here. That velocity field is conditional on the text. They do some classifier free guidance there. And then once they kind of do a couple steps of this rectification process, of which they describe here, then they simply just take this rectified Stable Diffusion model, and then they distill a student from it. So distillation is the process of taking a teacher model and then distilling a student from it. In this case, they're doing distillation for the UNet, and they're distilling the UNet so that rather than taking whatever 4 steps, they take 1 step. But so far, so good. I'm literally about to get cut off here, so I'm going to blow this horn and call it. Thank you, John, Every Dream, everyone else, Creative Builds, you, June. Hope you guys found this interesting. Hope you guys found this cool. Join the Discord, have fun, and do something cool with diffusion models today.